Today's video takes a closer look at a component that you might have used before or you might have seen on other people's projects. It's called an ultrasonic transducer. It's designed to be a microphone or a speaker for frequencies that are too high for humans or most other animals to hear. Most people probably haven't had a reason to use one of these transducers all by itself, but you might have used it inside one of these ultrasonic rangefinder units, like the Parallax Ping or one of these generic models from eBay. These two rangefinders use separate transmitter and receiver units. They're even labeled on this board. The way these work is the transmitter sends a little ultrasonic click that we can't really hear, and then it times how long that click takes to propagate toward some obstacle and bounce back, and then land at this receiver. You'll also see some rangefinders, like this one from Maxbotics, that uses a single transducer to transmit and to receive. This results in a design that's more compact and possibly even more accurate at the cost of somewhat more complex electronics. This is an older project of mine that uses one of these rangefinders as kind of a user interface, but you also see these a lot in robots to detect obstacles. Nowadays, LiDAR is starting to become a viable alternative, but these are still super useful, and it's nice to know how they work and how they might be modified. Even though the actual principle these operate on is identical, they really do have very different capabilities. The parallax sensor is really nice because it can give you a digital readout immediately when the echo is received, and then you can just time it yourself with arbitrary resolution. And the components are all well chosen, so you get a fairly stable output. And these little eBay modules, that you can find them, I think if you just search for this code, HCSR04, you'll find these. And they operate on a similar principle to the Parallax Ping. They're just kind of made much more cheaply all around, so the output isn't as stable. And then these sensors from Maxbotics, I really don't like them. They try to be clever, and they have a microcontroller that can be configured to send out results in various formats, including a voltage and a time and a serial message. But this is all after it's been quantized to 1-inch increments, so it's really no good at all for any kind of application where you want to sense something with some nuance to it. So here I've got some test equipment set up that'll approximately replicate the distance measurement technique that these little ultrasonic rangefinders use. And we can experiment with different frequencies and different speakers to see how it works. So the bottom trace is coming directly from the signal generator. I have it set up to generate a burst of sine wave pulses. In this case, 4 cycles, and then it stops for 100 milliseconds. Then the top trace is coming from this little microphone here. So let's plug in the speaker and see what happens. So the amplitude on the bottom trace goes way down because the speaker has 8 ohm impedance and the signal generator output is 50 ohm impedance. So the two act like a voltage divider and the speaker doesn't get that much voltage, but that's fine. Then on the top trace we can see that 1 kilohertz pulse is getting mixed in with all the environmental audio, but it still stands out pretty well. I can pull this away, and the amplitude decreases, but kind of more predictably the phase also shifts according to the speed of sound. So this would work, but the waves don't propagate very far and it's super annoying. So let's see if we can get the frequency up out of the human range of hearing. So as I start changing the frequency here, you can see the wave shape is distorting like there's a resonance nearby, and that sounds like it. You can even hear it getting louder. So it's right around there. We're hitting some kind of mechanical resonance in the speaker that's boosting our signal, kind of like a tuning fork. And after I get past around 9 kilohertz, it's much quieter, and the wave continues to shift in shape as it distorts a little bit. Right around 30 kilohertz now. I'm still hearing a click from the speaker, but if you zoom in, you can see kind of what's going on there. So I'm trying to drive the speaker here at 30 kilohertz, and the speaker seems to be responding to the DC component in this pulse, where it actually switches from off to a sine wave. And so I think that switch where it goes from DC to the sine wave is turning into the click we're hearing. And some of the 30 kilohertz is making it through, but really not very much. And there's so much distortion from that initial click that it would make it difficult to actually measure the 30 kilohertz portion reliably. 48 kilohertz, 55. Yeah, there's none of the ultrasonic is getting through at that point. So this is a short sine wave burst at 40 kilohertz. the same as one of these ultrasonic rangefinders would use. And we can see a little bit of that 40 kilohertz showing up in the microphone, but mostly it's just this terrible attempt that the speaker makes to respond to the pulse train showing up and then disappearing. If I drive the speaker with 40 kilohertz continuously, some of it makes it through, but it's very inefficient. It's finally inaudible, because now the speaker is no longer responding to the lower frequency components of the pulsed signal. So let's compare the speaker with an ultrasonic transducer. So right away we can see it's much more efficient at generating that 40 kilohertz pulse, and it doesn't have that terrible low frequency distortion that made the speaker annoying. So that's pretty good. You've got a nice strong field right in front of it. It seems to fall off after around 30 degrees, which is what most of these are specified for. Let's try changing the frequency to see how this one responds. You can see it looks like the transmitter really wants to ring at 40 kilohertz. If I give it a much higher frequency, then it almost kind of filters out most of it except for that 40 kilohertz energy that's left. Alright, hopefully the scope display isn't getting too crowded, but I added this new purple trace, which is a FFT, so the frequency domain representation of this received audio signal up at top. And so here the peak is right at our 40 kilohertz frequency that we're transmitting. Let's go up. Let's try to transmit a higher ultrasonic frequency than 40 and see what happens. So that peak is shifting down, and some of the energy is kind of moving over into the higher frequencies, but not very much of it. A lot of it is just that peak kind of moving to a different harmonic. So if you're familiar with this behavior, this will right away look like a resonator. This is basically acting like a tuning fork. It's designed to resonate at 40 kilohertz, and so if we help it out by sending it exactly a 40 kilohertz input signal, then a lot of that energy will make it through. But if we give it a different input signal, then very little of that makes it through, and it really just tries to convert that energy back into 40 kilohertz vibration, because that's what it's really designed to mechanically oscillate at. And here I'm down at 19 kilohertz, and so we're getting a little bit of that 40 kilohertz ring still, almost nothing at 19. So this would be a very bad general purpose speaker. Oh, now I can hear it clicking. That's interesting. Yeah, this would be a very bad general purpose speaker. It's really more like an electrically actuated tuning fork that just kind of vibrates at this one particular frequency. That said, people have made a particular kind of audible speaker using these transducers. If you search for parametric speaker, you'll find some interesting examples of that. This is another type of ultrasonic transducer I'm interested in. This one comes from one of those alarms you can put in your car that beeps if you're about to back into something. And it was really cheap. I think the entire kit of, a dashboard-mounted thing and 4 of these transceivers was something like $15 on eBay. I'm interested in these things because they serve a similar function, but rather than being kind of fragile and open to the elements like the traditional little metal cans, this one seems pretty rugged and waterproof. And the actual front surface of this thing is the ultrasonic emitter, which is pretty interesting. This is yet another different type of ultrasonic transducer. You might have seen these in an ultrasonic levitation video from Mike, of Mike's electric stuff. They're pretty interesting. They're usually used for ultrasonic cleaning devices, and so they're actually designed to operate at a fairly high power. But let's just see how they would compare to the little ultrasonic transmitter in this same circuit. So this whole contraption is actually designed to resonate at this very high frequency. So the energy that we're putting into this doesn't get us nearly as far because we have so much mass to move around. It does work as a transmitter. If I get it really close to the microphone, you can get a weak signal. After this initial energy has gone into kind of getting it started vibrating, you can actually see some back EMF from that vibration going back into the transmitter after the pulse has ended. In fact, that ringing lasts for quite a long time. Not a lot of actual energy gets through the system, just because the signal generator can't move so much mass without a lot more output power. But we do see just such a long kind of reverb tail as the resonator slowly dies down. If I squeeze the transceiver, then I can damp that much faster. And that also changes the frequency very slightly. So far we've seen these two transceivers that were clearly designed both to transmit and receive. But we also have these much more common devices where one transducer is clearly marked as a transmitter and one is clearly marked as a receiver. And normally I would have thought that this would just be a difference in the circuit layout and not in the actual transducers themselves. But when I tried buying these transducers individually, these really common, inexpensive ones that are used in all the ultrasonic rangefinders, they're only sold as transmitters or receivers, usually in pairs. So I'm curious what the difference is between these devices. From the outside, they look pretty much identical except for the stamped T and R. Alright, so here's the one marked receiver. Now if I switch to the one marked transmitter, that's very similar. It's actually slightly less. I've tested a handful of T's and R's from the same vendor and presumably the same batch. And they're very similar to each other, but in most cases, I think in all the cases, the R performs slightly better as a transmitter than the T. So maybe if you buy these, test them yourself and don't go by the markings. So the T, that one was an R and it seemed to have about a 30-degree angle. About the same here. So this is the same setup, but I've moved the microphone down here and turned up the gain somewhat. And now we can use this setup to measure distance. But you can see there's quite a lot going on the scope now. That top trace has just ambient audio from the room, and it has that kind of early transmission path directly from the transducer to the microphone. And then finally it has the signal we're actually trying to measure right there. Now we have pretty much the same setup, except that instead of receiving using a normal microphone, the receive side is just this ultrasonic transducer connected directly to the oscope. And now you can see the signal-to-noise ratio is way better. This is because both the transmitter and the receiver now are acting like selective filters that only really want to pass that 40 kilohertz signal. So at the mechanical level, actually, the receiver is ignoring the room noise, ignoring my voice. That gives this kind of a receiver much more ability to pick out signals in a noisy environment. You can filter out a lot of the acoustic noise mechanically before it even reaches the electronic preamplifier. If I rotate my hand, the signal pretty reliably reflects. There's always some part of my hand that's pointed roughly toward the sensor. But because there are so many different surfaces the signal can reflect off of, all of those different reflection paths merge together in the air to create an interference pattern that changes as I move my hand. So that's why the shape of the wave and the amplitude change so much, even if the reliable pulse at the same time can still let us measure the distance accurately. This piece of cardboard reflects the wave much more efficiently than my hand. It's big, flat. In fact, if I manage to hold this at just the right angle parallel to the table, you can see multiple reflections as the waves bounce again and again between the table and the cardboard. This technique of bouncing sound back and forth between parallel plates might remind you of a laser. This kind of resonant cavity is also how a microwave oven's magnetron tube is tuned. The nice reflections we get with the cardboard gives us a hint that maybe we can guide these waves using some kind of wave guide. This piece of vinyl hose works a lot like an optic fiber for this ultrasonic sound. So it leaves me wondering, how much could this technique be extended? Just like it's popular to put your surface mount LED on the circuit board and then use a light pipe to throw that light, directly where you want it on your product's enclosure. I wonder if you're building a robot, how practical would it be to put the ultrasonic transducer on the circuit board and then have features in maybe a 3D printed robot body that direct the beams all in different angles. Now we have the transmitter on the left aimed directly at the receiver on the right. The top trace's scale is exactly 1,000 times greater than the bottom trace. Here we're showing the transmitted signal with 10 volts per division and the received signal with 10 millivolts per division. As you might expect from how efficiently the cardboard seems to reflect the ultrasonic waves, not a lot of the ultrasonic energy would get through this piece of cardboard. On the other hand, if I completely cover up the transmitter with my hoodie, the amplitude only goes down by about half. The waves make it pretty well through cloth. This thin plastic cling film blocks about as much as the cloth. If I leave the film somewhat loose, then it transmits the energy pretty efficiently. Then as I pull it tighter, you can see it doesn't transmit as much ultrasound. And then if I pull it even tighter, now it actually starts to oscillate at a different frequency on its own. So I have the transmitter on a turntable, and right now it's aimed for maximum signal amplitude, which unsurprisingly is directly at the receiver. I continue to get some signal even way out here at 90 degrees. If you're lucky enough to find a datasheet for the transceivers you have, they might have a graph in polar coordinates showing you the power at every angle. And usually they drop off pretty sharply around 30 degrees. And these seem similar. It almost looks like they radiate energy just a little bit from the sides of the cylinder. So that got me thinking about making 3D printed objects that have space for a transducer and a built-in waveguide. So this one's just sort of a simple elbow joint. There's a 90-degree bend. The tube is about the same diameter as the end of the transducer. So if this design works correctly, I would expect this porthole to behave a lot like the original kind of opening on these transducers would. Yeah, so I mounted this with the transducer pointing that way, just as a control to see if this was successfully redirecting the flow of acoustic waves upwards. And I was still getting some kind of a signal, so I thought, oh, maybe it's radiating off of this flat surface. But if I cover the porthole, then I get nothing. So it looks like now the transmission amplitude is pretty respectable, and it definitely does seem to be aimed in the direction we expected it, kind of coming straight out of that porthole. So it does look like this 3D printed elbow joint seems to be working. But I did notice that the kind of off-axis radiation appears to be more spread out than with the original unmodified transmitter. It doesn't fall off quite as fast, and there's this kind of strange lobe right here, which does actually, that seems to be lined up with the corner, actually. If I turn the turntable to kind of maximize the wonkiness of that wave, so like right about there, then the corner of this box is aimed directly at the receiver. I think if I just rounded all the edges in this thing, it would probably perform pretty well. So this is the next experiment I wanted to try. I know I can just take these ultrasonic waves going down and redirect them out that way, 90 degrees, but this is a little bit more ambitious. This has a little cone in the center, so the idea is you aim the ultrasonic waves straight in, and the center of that beam hits the cone, and that disperses the waves 360 degrees, and hopefully it comes out these vents in a usable form. So I've tried to design this, not really knowing anything about proper acoustic waveguide design. I kind of went on intuition, and I tried to design this so that each of these little compartments, each little kind of vein, maintains the same area as it reaches the inside of this cavity, so they kind of change aspect ratio and become taller and more narrow. I'm hoping that means the pressure waves don't experience sort of an environmental difference that causes them to reflect. So, if we're lucky, then the ultrasonic waves efficiently bounce off the cone, then just spread out and exit through all of these vents. This is a tight pressure fit just to make sure there's a nice airtight seal and that it doesn't wobble its way out. That seats tightly against a lip in the interior that should set it at the right depth. Well, I'm pretty happy with that too. The output isn't as strong, but it seems pretty evenly spread all 360 degrees. So there are some specific angles that are basically dead spots, but they're quite small. This has managed to spread the energy out over quite a large range of angles. Well, that's pretty neat. This might be pretty close to an omnidirectional ultrasonic transmitter, sort of like an antenna. So as we've seen, all of these items are ultrasonic transducers. Mechanically, they're different, but electrically, they all operate on the principle of piezoelectricity, the same as these little discs. You might have seen these little piezoelectric discs in greeting cards or in other cheap electronic devices, but they're actually pretty marvelous. This common piezoelectric buzzer is a sandwich of materials. On the bottom, any kind of flexible metal, in this case brass. On the top, a very thin layer of silver or any other conductive material. But in the middle, that's the piezoelectric material. You might have seen the initials PZT. Some people will tell you that stands for piezo transducer, but really those are the initials for the chemical compound that makes up most piezo transducers, lead zirconium titanate. Piezoelectricity is a relationship between mechanical strain and an electrical field potential. So in this case, by applying a voltage across the piezo crystal, it'll actually grow slightly. And because it's bonded to this piece of metal that won't grow, it causes the whole thing to flex like the head of a drum. These piezo discs also use mechanical resonance to amplify their sound, but they tend to be tuned for the audible range. This electronic whiteboard marker we looked at in an earlier video uses a thin film polymer transmitter. But these other ultrasonic transducers probably use the same PZT crystals that this simple buzzer uses. Because this transducer is so large, it's easier to see the components. We can see here two layers that have probably some elastic properties to them. But most importantly, there's this layer of piezo ceramic material, probably several stacked layers actually. And when you apply voltage to those layers, they'll expand and drive the mass a little bit in one direction. And then the elastic will pull it back, and it'll set up a mechanical oscillation. And then by adding energy into the system at the same frequency as the mechanical oscillation, you can drive a continuous wave, a continuous vibration, actually really efficiently. This isn't designed to transmit energy into the air. It's designed to bolt onto something and vibrate that thing. I mean, it will transmit energy through the air, as we've seen, but it doesn't really do that especially efficiently. So that leaves us with these two. And these are both designed to transmit 40 kilohertz waves through the air. So a transmitter like this would really be no fun to use, outdoors. Anything gets in there and it probably just stops working completely. So the automotive transmitters are designed somewhat differently. This whole front plate you can feel it actually ticking as it transmits. So this must actually be directly above the piezo element. But then it's also somewhat mechanically isolated from the exterior of the housing here. And it looks like there's some kind of rubber piece in between that is probably actually providing a weather seal and giving the interior bit a little room to wiggle. I'm curious if we can see any internal differences between the T and the R here. From the outside, they sure look the same. Now, we could brute force this, stick it in a vise, get the Dremel, just cut through the side here. But I'm interested in seeing if we can take this apart the way it was put together. So I wonder if we can get this out easily just by unbending the edge of this tube. This might be easier than I thought. The metal is pretty soft. This looks like it's answering some questions, but maybe asking some new ones too. Oops. The screens are just held into the front of the tube by this little metal ring. So the transmitter and receiver both work fine with the case off, though we can see they have a somewhat wider radiation pattern. Here's a much closer look at the transducer marked T for transmit. You can see the plastic base holds the two sturdy pins in place, but then two very fine bond wires carry the electrical signals up to the actual piezo crystal. So the piezo crystal is going to be somewhere inside that larger disc area, but that little metal hat on top seems to be sort of like a horn that pushes the air as the transducer moves up and down. The vibrations in the transmitter are much too subtle to see, and they seem to be too subtle to move around something like this plastic bead. But if I touch the piezo transducer or this vibration spreading cone with my tweezers, you can kind of hear it screech as the two things vibrate against each other. This is the one marked R for receiver. So far I've noticed two differences. One of those leads has been pushed up a little bit, and it's almost touching the piezo transducer, but that might just be something I did to it during testing or disassembly. It might not be a manufacturing defect. The other difference is in the shape of this little resonating cone at the top. So over here on the transmitter again, that little resonator on the top is just a little stamped metal cone that looks like just kind of a perfect little horn to push the sound waves up into the air. But over here on the one marked receiver, it looks like they've filled that cone in with just a drop of glue, just a drop of, clear epoxy or something. So I wonder if this serves to change the shape of the kind of sensitivity pattern, or whether it kind of damps out extra vibrations after the pulse has been received. And it's kind of strange that this one seemed to be just a little bit better at transmitting than the unit without the drop of glue. So probably because this is one of the cheaper transducers, instead of a metal plate with sort of a feed-through gasket for one of the wires, this is really just a plastic plate with this tiny thin layer of metal on top that isn't even electrically connected to either of these legs reliably. So if we put that aside, then we're just left with this plastic assembly with the actual ultrasonic transducer mounted on it. So this disc where the horn is mounted seems to be the metal backing plate for the piezo transducer. And then on this side, you can see a little hint of the electrodes and the kind of yellowish piezo ceramic material. Alright, I'm not worried about breaking the bond wires or this plastic piece, but I would like to do this without breaking the piezo crystal if I can. It looks like this is stuck onto the plastic base with kind of a silicone putty. So here's what's left at the bottom plate. Now we can get a much clearer idea of how this was put together. The piezo crystal was attached to this plastic base plate using kind of a flexible silicone adhesive. And the base plate holds it only at the edge, leaving the middle free to swing up and down. So here's that tiny ultrasonic transmitter cone again. And now that we've removed it from the supports, on the opposite side, we can see our familiar little piezo disc. So again, we have a metal piece on the outside. In this case, it looks like it's steel. And then the kind of yellow PCT crystal, and then the silver electrode and tiny wires connecting them to the pins. So that was the transmitter. Let's take a look at the receiver and see if we can notice any other differences. Well, so far it looks the same. There's the drop of glue inside the cone like we saw before. And on the other side, it looks like they might be using a little bit more silicone goop, but that's probably just unit-to-unit variation. Doesn't really look like this is substantially different from the transmitter. Alright, I had one last thing to tear into in this video. These inexpensive automotive ultrasonic transducers. I'm not sure why they bother telling you which side is up. Maybe it's a weatherproofing issue? In any case, it looks like this cylindrical piece kind of fit inside of a outer plastic shell, probably press fit with some snaps. I'm going to see if I can wedge it out through these little rectangular slots. There's a plastic cover that seems to come off pretty easily if you wedge these plastic slots open. Alright. Well, that reveals a whole load of silicone sealant goop. Looks like that center hole in the back panel was an injection port to fill the whole back side with silicone. I'm just going to cut this to make it easier to deal with. So this is actually pretty close to the end of the wire. The silicone sealant just barely covers the gap between the cable and the insulation. And actually it looks like this is coax, which is nice. I think at this stage we might be better off just peeling off the outside of this casing. I can already feel the inside and outside of this cylinder separating. So that outside piece is just all coming off together. So this was just kind of an outer shell to hold everything and kind of wedge it into the bumper of your vehicle. And then this silicone acts as a shock mount for the interior ultrasonic transducer. And then it's all been kind of sealed in the back with silicone goop. Oh yeah, it seems like it peels open on the front. Yeah, it's just like a little silicone boot that this little metal can fits into. So it looks like there's a tiny circuit board back here, which might just be... I kind of doubt there are any electronics on there. That's probably just for terminating the coax. But it looks like the coax terminates to a tiny circuit board. And then there's a little wire for the center connector running to the actual transducer body. There's a metal spring clip connecting the ground on the coax to the exterior of this can. So just so I can separate these two without too much damage to either, I'm going to cut this little wire in the middle. So now we have this transducer body with just a metal can for one electrode and this little wire. Well, this tiny circuit board doesn't have any components. It was just part of the coax termination. So all the way in here we have the same kind of silicone that we saw on that very outer seal. You know, a little bit crumbly, but it feels kind of like, you know, basic weather sealant. So right underneath that white layer of silicone sealant, there's a layer of this kind of brownish material that might be some kind of glue or some kind of other elastic. The brown material is... that's very strange. It almost reminds me of cork. Could they have just filled this with sawdust as a kind of, elastic or like damping medium? Maybe this is cork for moisture absorption, like in case any water gets all the way back here. Oh yeah, this is a cork. Ha! So there's a small pad of cork material that might have been for moisture purposes or for springiness. Yeah, now we can see where that wire is actually soldered to the piezo crystal. Between the cork and the piezo crystal is this kind of soft donut of felt. This might have supported the crystal a little bit more gently along the edges while still allowing it to vibrate in the middle. So now we can see our old friend again. It's the same kind of little PZT transducer, but this time much tinier. So this whole piece that we're left with after pulling out all the layers of spacers and fillers, it seems to be just a single piece of turned aluminum, painted black on the front, and then on the inside we have the little tiny PZT disc bonded to it. This is a pretty interesting design. It seems very kind of rugged against the environment, and also it seems to produce a pretty strong acoustic vibration. That thing is pretty powerful. I'm getting waves all the way over here. Well, thanks so much for watching. I hope you enjoyed taking a closer look at the electronic components that make these common distance sensors work. And I hope it might have given you some inspiration to use ultrasonic transducers in some new ways, and maybe come up with some new ways of using sound that we can't hear in order to measure things or otherwise kind of make people's lives better or more fun. So thanks for watching, and if you enjoyed this, maybe check out some of my other videos or subscribe, and you'll be the first one to know when I post something new. Thanks!